All right, let's jump straight back into this explainer and knock out the second half of our power quality audit. We're continuing our deep dive into Singapore's high-voltage engineering regulations, moving from the foundational concepts we looked at before right down into the microscopic details of the electrical waveform itself. If you've ever wondered exactly how clean the electricity needs to be before it's allowed onto the grid, well, you are in the perfect place.
So in part 1 of this explainer, we hammered down that strict 0.85 power factor efficiency floor for high-voltage consumers. We saw that dropping below that floor essentially means you're wasting transmission capacity on reactive power. But that leaves us with a huge question. Aside from just being efficient, how clean does the actual electrical waveform need to be? And on top of that, how evenly does that power need to be distributed across the 3 phases?
We measure that cleanliness with something called total harmonic distortion, or THD. Basically, THD calculates how far your power strays from a perfectly smooth, pure sine wave. This distortion happens when one or more harmonics get added to the fundamental frequency. You can honestly think of it as a type of electrical pollution that quietly but really severely damages equipment over time if we don't keep it in check.
And the regulations tackle that pollution with a very strict THD ladder right at the point of common coupling. It steps down tier by tier. At the extra high voltage tier, it's capped at a super restrictive 1.5%, where, by the way, odd harmonics cannot exceed 1.0%, and even harmonics are tightly capped at 0.5%. From there, the limit moves to 3.0% at 66 kilovolts, 4.0% at the 22 and 6.6 kilovolt medium voltage tiers, and finally caps out at 5.0% down at low voltage.
Now here is a massive, counterintuitive twist that catches a lot of people off guard. As the voltage drops, the THD limits actually get looser. Yeah, it's literally the exact opposite of what most of us instinctively assume. Usually, you'd think regulations get stricter the closer you get to the end consumer, right? But here, the lowest voltage actually gets the highest allowance for distortion.
So why on earth are the rules written this way? Well, the logic is actually pretty brilliant. Electrical distortion is the most dangerous where it can travel the furthest and mess with the most connected equipment, and that happens at extra high voltage, the absolute backbone of the grid. If distortion runs rampant at 400 kilovolts, it's going to propagate across the entire network. So the regulatory leash absolutely has to be tightest at the top of the grid to protect everything downstream.
To really lock this whole power quality concept into your brain, think of the grid like a massive symphony orchestra. Your power factor is the wasted backstage noise, energy that never actually makes it to the audience. Your total harmonic distortion, that's the instruments themselves playing completely out of tune, just ruining the pure sound of the music. And finally, phase imbalance is like having uneven volume between the sections, like the brass completely drowning out the strings.
Speaking of uneven volume, that brings us right to phase imbalance, our final audit parameter. The rules say that planned outages, or even just standard operations, absolutely cannot cause the maximum negative phase sequence component to exceed 1.0% of the phase voltage. It is a razor-thin tolerance, and it exists purely to ensure all 3 phases stay in perfect harmony.
Let's test this out in the real world so you can see how it applies to daily engineering decisions. Imagine you're auditing a 22 kilovolt feeder connection for a brand new facility. You take a reading at the point of common coupling, and your meter shows 4.6% THD. Based on that regulatory ladder we just talked about, is this connection compliant? Think about those tiers for a second.
No way. That is a hard fail. Because you're in the medium voltage 22 kilovolt tier, the THD limit is exactly 4.0%. So a reading of 4.6% isn't just a minor drift, it's an outright regulatory violation. As the engineer, you cannot submit that connection for approval. You'd have to step in and design a harmonic filtering solution to clean up that waveform before SB Group even lets it near the grid.
And just like that, the regulatory groundwork is complete. You now have the complete toolkit to expertly audit any connection's microscopic power quality data. You've got your steady-state voltage variation limits of plus or minus 5% at 400 kilovolts and 6% everywhere else. You've got your power factor floors, that THD ladder, and your phase imbalance cap. You are fully equipped to assess the health of the power before a single switch is ever thrown.
All right, so you've mastered the micro-level waveform rules. Now we are going to pivot outward to the macro-level physical grid architecture. Because let's be real, all that incredibly clean power means absolutely nothing if the physical grid goes down. Everything we've discussed so far is anchored by one absolute foundational fail-safe philosophy for Singapore's transmission network. The grid must survive any single loss.
Enter the single contingency, or the N-1 criterion. This isn't just a suggestion, it's a completely non-negotiable planning standard dictated by the transmission code. It requires Singapore's high-voltage grid to instantly absorb the sudden, unexpected loss of any single major piece of equipment. If a massive generator trips offline at 3 a.m. or a 400 kilovolt transmission line just severs, the system must withstand it. Every single time.
And withstand it has a very specific, legally binding meaning here. On a small, densely interconnected island that has absolutely no overland backup power to import in an emergency, the N-1 rule guarantees that one exploded transformer results in exactly 0 cascading failures, 0 system instability, 0 load shedding. The lights shouldn't even flicker for the end consumer.
But here's the catch. Getting that level of reliability costs serious money and effort. It literally requires building extra quote-unquote wasted transmission capacity that the grid hopes to never actually use. It's purely physical insurance. Which leaves us with one heck of a question to wrap up this explainer. If we are designing a massive system to seamlessly reroute power in milliseconds and totally mask a catastrophic failure, how exactly do we construct that physical underground architecture in Switchgear to guarantee it never, ever fails? We're going to unpack exactly how they pulled that off next time.